Hello. So today we are going to talk about superconductivity. So again, this will have 2 lectures on superconductivity. So let me get started here. Okay, superconductivity. So we'll start first talking about normal state behavior in metals before it becomes superconducting. So then we'll talk about hallmarks of superconductivity, 3 important properties so that you would expect in a superconductor. So first thing is zero resistance. Everybody's familiar with that. So below this transition temperature, so the normal material becomes superconducting, then your DC resistance go to 0. So second one is perfect diamagnetism. That means your the susceptibility will be perfectly -1. So we'll talk about that one. So you have the exclusion of your magnetic field from the interior of the superconductor. So third thing is magnetic flux quantization. So that means if you have a ring structure of superconductor, so the flux through that ring structure will be quantized. So you have some quantized values of this something called the fluxoid. So these are the 3 hallmarks of superconductivity. So lastly, I will talk about some phenomenological theory of superconductors, mostly London theory. So then the Ginzburg-Landau theory. So that introduced something called these 2 length scales, the penetration depth and the coherence length. So that differentiate the superconductors by type 1 and type 2, depending on these 2 length scales. You have type 1 or type 2 superconductors. Okay, so like I said, the 3 hallmarks of superconductivity. The first one is zero resistance. So if you pass a current and measure the voltage, so then you can measure the DC resistance. You can see here resistance has some finite value, but at this transition temperature it goes exactly to 0. So but the transition is not as sharp as this one, so this is some schematic. So you will see some not that sharp transition in real superconductors. So second one is the complete diamagnetism. You can see here when it is in normal state, if the superconductor is not superconducting, so it's in a normal state, then the magnetic field will pass through the superconductor. But if you cool it down to below your transition temperature, now it is superconducting, then you will not see a magnetic field inside the superconductor. So that we call the exclusion of your magnetic fields. You can see magnetic field lines will go around the superconductor, but not through the superconductor. So that means your magnetic induction, so that B value, that goes to 0 at this transition temperature. So that means your susceptibility is -1. So then H and M, the external magnetic field and magnetization, they are equal and opposite, so they cancel and the B field becomes 0. So third one is if you have this ring kind of structure, the flux through the superconducting ring, so the flux is actually magnetic field times area, right? So that flux is quantized. So that's n times this some constant called fluxoid, that is h over 2e. We'll talk about that one later. So these are 3 hallmarks of superconductivity. So actually this zero resistance thing was first observed, like shown in the right graph here, when Kamerlingh Onnes measured the resistance of mercury at 4.14 Kelvin, that is almost at the boiling point of liquid helium. So he saw this resistance, finite resistance, immediately going to 0 around that 4.15 Kelvin. So that's the first observation of this zero resistance of DC resistance. But you should realize that if it is for AC impedance measurements, so that resistance is not exactly zero, it will be finite. So then, so it was difficult to explain the behavior of superconductivity in terms of ordinary electron properties. So then that's how they started thinking about real theory behind superconductivity. So they came up with the idea of Cooper pairs. So Cooper pairs are like these two electrons, they are coupled together. So usually electrons, they have negative charges, so they don't want to come together, right? So they are getting repelled, but due to some mediation with the phonons, so you'll have more attractive interaction greater than that repulsive force, so that keeps these two electrons together. So they are, we call Cooper pairs. So the Cooper pair is the basis for the superconducting properties. So they have momenta in opposite direction, so that will help you to move these Cooper pairs without any dissipation of heat. So if you look at in the diagram in the right, you can see Cooper pairs, they are at the lowest energy state. So then we have something called the superconducting gap, like delta. So if your energy is higher than that superconducting gap, this Cooper pair will be disintegrated. Then it becomes like quasi-particles of like electrons and holes kind of situation. This quasi-hole excitations, these are quasi-particle excitations. So the total energy required to break these Cooper pairs is 2 times this superconducting gap. So we'll talk about all these things later. So we talk about this perfect diamagnetism. If you want to understand that, you can see if you are superconductor below TC, now it is superconducting, you have this external magnetic field. It cannot go through the superconductor, so then it has to go around. So that means your total magnetic field inside would be 0. So we know B is given by mu 0 H plus M. So then in this case, your M is exactly negative H, because that's your perfect diamagnetism means your susceptibility is -1. Then your B field will be 0. You can see here on the left figure, you have when it is in normal state, magnetic field is going through. Below transition temperature in the superconducting state, so no magnetic field inside the superconductor. So this is more like exclusion of magnetic flux. So this is the reason why we can have this levitation of superconductors, levitation of magnets, right? If you have superconductor, so we'll talk about that one later. So that's all because of this Meissner effect. So actually, there have been some practical applications of this one. So if you remember this, Japan, they tested this magnetic levitated trains, right? So achieving speeds very high, like 340 miles per hour speeds, because you don't have direct contact with the surface here. So if you look at this, we say magnetic field is inside 0 here, but if you look carefully, so that magnetic field inside the superconductor doesn't get immediately 0. It has to go through certain this thickness. So during that thickness, it's gradually getting smaller, the magnetic field, and in interior it becomes 0. So that the depth of that, or the thickness of that, we can say this layer, we call the penetration depth. So you can see here in this picture, I draw B as a function of this length along the magnetic, the superconductor. You can see in the outside you have some finite this B value. So, but inside you can see it's decreasing at a length scale given by this lambda, the penetration depth, it goes to 0. So it doesn't immediately goes to 0 at the superconductor surface. So you can see here this lambda. So after that lambda, B goes to 0. So then also this this penetration depth actually depends on the temperature, even below Tc. If you have Tc here, that lambda actually diverges exactly at Tc, but when you go to lower temperature, it saturates at this lambda 0 value. So lambda is also independent of the frequency. That frequency should be less than 2 delta, right? So because if it is more than 2 delta, you are going to break the Cooper pairs. So that penetration depth, this behavior is expressed in this expression here. Lambda LT is lambda L0 divided by this square root function of this 1 minus T over Tc to the power 4. So that gives you this behavior here. We'll talk about all these things later. So then what are the limitations of superconductors? So we know in temperatures, so at high temperatures above Tc, they are no longer superconducting, right? So only below Tc, they are becoming superconductor. So here actually we have this something called traditional superconductors. They have this Tc are very not too high. So this one actually is for later they discovered something called the high Tc superconductors, right? So in ordinary superconductors, usual Tc values are around 20 Kelvin or something like that. We'll talk about that one later. So anyway, important thing is your temperature should be below your Tc in order to become a superconducting. If your temperature is above Tc, so that becomes normal state. So another thing is magnetic field. So magnetic field also, if you have your magnetic field larger than something called this critical field, so then it becomes normal. So below that critical field, it's superconducting. So that means if you apply much higher magnetic field, you kill the superconductivity. You can see this the high Tc superconductors, they are actually type 2 superconductors. So for them, there's another field called this this Hc2. So above that one, it becomes normal. Between this two, there's some mixed state called this vortex states, and we'll talk all this about that. Third thing is the current. So if you apply some current larger than the critical current, so you kill your superconductivity. So it's superconducting only below its critical current. So you can see standard, so niobium, so they have this superconducting state below this critical current of these values. You can see this type 1 superconductors, so and type 2 superconductors. The critical currents are not too different, right? But for temperatures, so for high Tc or type 2 superconductors, that critical field is much larger than this type 1 superconductors. So then also magnetic fields also. So you have this second critical field for type 2 superconductors. We will be talking all these things in these two lectures. So when you look at your periodic tables, you find most of your superconductors in this shown in this blue squares here, like beryllium, aluminum, so the titanium, vanadium. So famous one is niobium, lead. These are standard superconductors at ambient pressure. The ones shown in green, they become superconducting when you apply very high pressure, like cesium, barium, yttrium, boron. So this can become superconducting only under very high pressure. So, but this was then also the people found some alloys of superconductor, like famous ones are like niobium tin. So then even this alkali metal dope C60 fullerenes. So there are many alloys. They showed superconductivity. So then also these standard superconductors, they could explain the behavior using this something called the spin singlet pairing. So when you have these two electrons pairing in the Cooper pair, so they will make it in singlet pair. So mostly in the S wave, that means your total angular momentum is 0, and you have total spin also 0 in the singlet state, right? So later in the type 2 superconductors, they found D wave singlet state. So that means you have L equals 1 situation, D wave. Okay, these are the superconducting elements we were talking about. If you look at these things, you can see it's a critical temperatures. They are showing, so there are two numbers on each superconducting element. So the one on the top one is that critical temperature. You can see they are very small numbers, except for this niobium. Niobium has about 9.5 Kelvin. So others are less than niobium. That's why niobium was very special those days. So see, you can see mercury has 4.153 as measured by Camelin honors. So then there's this one shown on the bottom. That number is this critical field. So that is in millitesla, like 10 millitesla. So again, you can see they are not very high. Niobium still has very high this critical field, like 198 millitesla. So that's still pretty not very high value, right? So if you look at these things, you can see transition temperatures and critical fields are generally low. They are not very high, right? So they all are less than 10 Kelvin and less than 20 millitesla. Then also, except for this, the niobium has the highest among these elements. That has the highest TC about 9 Kelvin and TC about 200 millitesla or 0.2 Tesla. So one thing you should understand is metals with highest conductivities are not superconductors, right? Things like these copper, silver, gold, these are good electrical conductors, but they are not superconductors. So you have to understand best electrical conductors are not necessarily superconductors. And also the transition metals like this 3D transition metal, chromium, manganese, iron, cobalt, nickel, they are supposed to be not superconducting, because we know superconductors and magnetism, they are not compatible, because by applying magnetic field you kill the superconductivity, right? But that was the understanding at early times, but that was not the case. Later they found superconductivity of iron that has TC about 1K, but at very high pressure, about 20 gigapascal. So this was discovered in 2001. So then later they found superconductivity even in lithium. So, but they are very low TC, about 0.1, 0.4 millikelvin. So even lithium became superconducting. So like I said, the theory behind superconductivity was not very clear. So people try to explain everything in this Cooper pair point of view, and also Landau and Ginsburg, they proposed some phenomenological theory based on this London's initial this penetration depth related theory. So then actually most decorated theory was developed in 1957, I guess, by Bardeen, Cooper, and Schrieffer. So they call the BCS theory. So they explained that one due to Cooper pair, and they developed the wave function for Cooper pairs. So then again, that is, like I said, is a S wave pairing. So that means your S means you have total angular momentum 0. Then also this has singlet, right? So if you remember, singlet means you have your these two Cooper pairs with spin up and down, so you can have total spin 0. So the triplet state has any of these three states, they have spin 1, right? So that's triplet state. So total spin 1. So here they assume, so this is S wave and singlet pairing. So what is the theory behind this BCS theory? Actually, you can understand like this Cooper pair. How does Cooper pair sits together? Because two electrons are supposed to repel each other, right? So the way they explain was, if you have this, suppose you have a crystal, like these atoms in the crystal. So when the Cooper pair is moving through the crystal, so this one spin of the one of the electrons in the pair, so that will distort the atoms in the lattice, right? Because lattice has this atom, so that this electron will attract some of the Coulomb interaction or repulsion. So you will distort some of the atoms, so they can become positively charged here, right? So then your crystal becomes kind of distorted. So or you can say electron polarizes the lattice, because electron has negative charge, so that will polarize the atoms in the lattice, so they become positively charged. So now this polarized lattice, so the second electron of the Cooper pair, so that will pass through that already distorted lattice, right? So second electron is now attracted to the concentration of positive charges. So that's because this one polarized and making that is positively charged. So then the second Cooper pair, that is also electron negative charge, that is going to be attracted to the this already polarized lattice. So that means now you have attractive force because of that interaction from the polarized positive charges. So this the attraction is actually greater than the Coulomb repulsion. So that's why we can say this this is, you can think in terms of phonons, right? Any lattice distortion is we call it a phonon. So this we can say this interaction is due to the electron phonon interaction. So that electron phonon interaction is greater than the Coulomb repulsion, making the Cooper pair binding energy. So again we know this 2 times that the superconducting gap is the energy required to break the Cooper pair into its electrons and holes. So we call the quasi-particles. So Cooper pair size you can estimate using the simple the Heisenberg uncertainty principle. So if you use delta E times delta T or even delta P times delta X is greater than H cross over 2. So if you use that one, you can find this Cooper pair size is simply VF H cross over delta. That's very simple to show. So like I said, so we started superconductivity, temperature about maybe 4.12 Kelvin, then lead. So then niobium showed about 9 Kelvin. So then by alloying with even niobium tin, you could get close to 20 Kelvin. So then it went a little bit above. So not until like 1985 or so they found this lanthanum barium copper oxide, this ceramic compound oxide. So that showed superconductivity close to 40 Kelvin. So that was a big discovery, because people never expected the TC to be that high, close to 40 Kelvin. Then there was a lot of effort at this point to try similar materials replacing these elements by every possible element in the periodic table. Then all of a sudden, around that time, they found Tc around 90 Kelvin for this special material called YbCO, this yttrium barium copper oxide. So that's the first time you could see Tc above boiling temperature of liquid nitrogen. Liquid nitrogen has boiling temperature of 77 Kelvin. So they found something around 90 Kelvin. That was the biggest discovery, right? Because now you have superconductors, you can study with liquid nitrogen. Previously, you needed liquid helium, right? So liquid helium boiling point was 4.2 Kelvin. So liquid helium is expensive and also hard to use because they evaporate so fast. So then liquid nitrogen is much cheaper and also easy to handle. So that started a new activity in superconductivity. So after that, people were trying to put even more component into the system. So then they could reach even close to 140 Kelvin. So at the moment, even with high pressure, I think people have reached around 200 Kelvin. So that's a very exciting period for superconductors around between 1980s and 90s. Okay, so this is where the nitrogen limits was overpassed, right? So that's a big discovery. Actually, this structure is you have these copper atoms and the oxygen atoms. So then in between you have the yttrium and barium atoms. So this is actually superconductivity mostly coming from this two-dimensional plane of copper and oxide. That's why they are called cuprates. So again, but these high Tc superconductors, the theory is different. So this actually, it's no longer S-wave pairing. So that's supposed to be D-wave, but still spin singlet because we know it should be singlet, right? So this L equal total angular momentum is 2. So this after yttrium barium copper oxide, then people started working on this thallium barium calcium copper oxide. So they have even little more high Tc. So these structures, you can see they are layered structures, quasi two-dimensional of this copper oxide films. So the copper and oxygen cuprate is the major thing. So that's a quasi two-dimensional, but they all have anisotropic physical properties because we know along the z-axis and xy they have different properties. These are ceramics, right? These are oxides. So that means they are in nature they are brittle and very poor ductility. So then also this oxygen content is very crucial. That's why we write like 7 minus delta. Even small change in your delta can change the superconducting properties. Okay, so then in recent times they found a new kind of superconductor called magnesium diboride, but they don't have very high transition temperature. They are about maybe 38 and some close to 40 Kelvin, but the origin of that superconductor is little different. So you can see magnesium in this square or rectangular plane. So then you have boron in this hexagonal rings, right? So this is the band structure of magnesium diboride. So here actually this we call two-band superconductors compared to ordinary superconductors. They are single-band superconductors. Here we are talking about interacting two or more bands. I think we are talking about sigma and pi bands, right? Because we have this hexagonal boron, they have sigma bonds and pi bonds, right? Perpendicular to the plane. So this by interaction of the sigma and pi bands, so they have this multiple energy gaps. So we call the sigma and pi gaps like delta. So that gives you some new theory of superconductors. Okay, so let me talk a little bit about the historical development of this superconductivity. This beautiful story started by this Kamerlingh Onnes by liquefying liquid helium. He first liquefied liquid helium, then because of that, this is a liquefaction system. So then he managed to measure the resistance of mercury. Then he discovered the transition temperature. So then that's the birth of superconductivity, right? So for that he got the Nobel Prize in 1913. So before we go into more details, I want to talk a little bit about some physical properties of superconductors. First thing is, if you look at this figure here, one thing is we know your resistance, so it goes decreases more like a metal, then all of a sudden it goes to zero, boom. So that's you have TC. When if you measure the specific capacity, so specific capacity, we know specific capacity for most of the metals at a high temperature in a normal state, the CV is proportional to T, right? So it's have this linear T behavior. Then at this TC, there's a sudden discontinuity here. So then it follows as exponential decay of your CV going like E minus delta over this your TC value. So this one physical property. So other one is, like I said, your resistance goes to zero at your TC value. You can see they are not like directly fall into zero here, right? But if you do it at different magnetic fields, you can see then your TC becomes even low, right? So this is for your zero field value. So then if you go to very high, like 9 Tesla, you can see your now TC becomes much lower. So this is one of the high temperature superconductors. So then you can measure your temperature dependence of your magnetic field. You can see you have these critical fields for as a function of temperature. So this is your TC and this is your critical magnetic field. So then if you look at your magnetization, so we know if this is actually negative magnetization. You can see for superconducting is a perfect diamagnetism, then M equals minus H. So then if I plot this minus M, M versus H, so minus M. So then you find this M equals minus H like this, right? So then above TC is no longer perfect diamagnetism, then it becomes almost zero. This is, we know diamagnetism for normal materials, they are very small, right? So they are almost zero. So this is what we expect. So then if you look at this critical field, like we do here, where the superconductivity lost. So also here superconductivity is lost about TC. This is your critical field. So this is the range you have superconducting state. This is the place you have normal state. So yeah, this is what we call critical temperature, and this critical field is given by this equation. So that's the behavior of this one. Then 1933, so Meissner effect was discovered at work of both Meissner and Ostenfeld. So they discovered this perfect diamagnetism. So your magnetic field is excluded from the superconductors. So magnetic field does not penetrate the sample. So that's we call is a ideal diamagnetic and also ideal conductor. So ideal conductor, superconductor, diamagnetism means you have chi is minus 1. So then 1935, little bit after this Meissner effect, so this London brothers, they came up with this simple theory. So they use this Maxwell's equations. So we'll get back to that later. So using that, he could explain how magnetic field is going to be penetrate through a superconductor. So he came up with this equation. Your magnetic field is exponentially decaying with this penetration depth delta. Then also he showed even the current also similarly decaying through the superconductor. That's the supercurrent, right? So then 1937, there's a new phenomenon was discovered for liquid helium. So that was very interesting because so for liquid helium, that's a bosonic particles, right? So you have two neutrons and two protons in your nucleus. So they have 0 spin, so they are bosons. So when you cool this liquid helium below some temperature, it's called the lambda temperature. So because liquid helium boils at 4.2 Kelvin, right? But if you cool little bit below 4.2 Kelvin, actually that you can easily do by pumping on the system, right? If you pump on liquid helium, you reduce the vapor pressure, so that will reduce your boiling point. So then you can cool it to further lower temperature. So if you do that one, so they found there's something called lambda point. So that is about 2.17 Kelvin. So below that temperature, this liquid helium becomes superfluid. Superfluid means there's no viscosity for the flow. So they can flow without any viscosity, without any impedance, right? So that means if you look at here, so we have some kind of two glass plates with liquid in a liquid helium bath here. So when you cool this below that lambda point, immediately you will see this liquid helium will start flowing through this inner tube like that. So this means there's no resistance for the flow. So they can, this surface of the wall has no resistance for the flow of the liquid helium. It can go without any viscosity. That's the property of your superfluidity, right? So superfluidity, then you can think about, you have the density of your normal helium and also superconducting helium. You can see how the density fraction changes. So you can see superconducting region density is higher for temperatures below Tc. So this almost all are superconducting. So but high temperatures, so above Tc, your normal density fraction is increasing, right? So here low temperatures superconducting, rho s is the density of superconducting particles. So rho n is density of normal. So that's a non-superfluid state. So then people measured the heat capacity of liquid, this liquid helium. You can see around this lambda point, that's about 2.17. So you can see how heat capacity is sharply going through some phase transition, right? So you can see here normal state, so normal flow. So then all of a sudden it becomes superfluid. So here are some data for different situations. So that's another, because superfluidity has very big similarity with superconductivity. You can understand why. So actually, when you go to helium-3 also shows the superconductivity, but helium-3 is a fermion particle, right? Because helium-3 has only 2 protons and 1 neutron. So that means they have spin half, so they behave as fermions. So that then you have 2 fermions. So that's very similar to having Cooper pairs, right? You have 2 electrons, they are 2 fermions, right, in the Cooper pair. So helium-3 superfluidity is very analogous to Cooper pair superconductors. Then in 1950, Landau proposed this phenomenological theory based on second order phase transitions. So what he did was he introduced this some order parameter. Actually, order parameter is some complex number. So that's the magnitude of psi squared is very small. So then he introduced this difference between the superconducting Gibbs energy and the normal state Gibbs energy. That difference is given by some constant A times this order parameter squared plus B over 2, this fourth power of this psi. So with this one, actually, if you look at this equation, so if A is greater than 0, so there's a G bar, that is the difference between GS and GN. So if A is greater than 1, this shows some 1 minimum parabolic behavior. But if A is a negative number, so this shows like 2 minima and 1 maximum, right? So like this one. So then you can actually so A should change the sign at the transition point. That's the whole idea, right? If you have some specific A, you can see how if you have some transition point, so that is determined by the sign of this A. So if you introduce, he introduced this quantity called tau, so that is given by this T any temperature minus Tc over Tc. So then we know at near Tc, so this tau is very small, right? So because we are talking about close to Tc value. So then if I introduce another parameter called alpha, so alpha is a positive value, so I can write A as alpha times tau. Then for T greater than Tc, so that means your tau is positive, right? So then your psi is 0. So if T is less than Tc, then tau is negative number. Then your psi squared becomes minus A over B times tau. So you can easily calculate this one. So that is mostly what is psi at 0 value squared. Okay, so we'll talk this one in more details later. So this is psi equals 0 situation is shown here. So because your A is negative, right? So sorry, in the first case A is positive. So here A is negative case here. Then at the same time, so Ginsburg joined Landau, and he introduced additional term into that. His the change in his this Gibbs free energy. So he introduced additional term due to the magnetic field. So he introduced, this is called this Hc squared over 8 pi. So Hc is the critical field. So then also he introduced this gauge invariant combination. You can write your momentum in your equation, like typically we write your momentum in quantum mechanics minus I h cross grad. So now, so he introduced additional term given by 2E over C times A. We discussed this one under magnetism. So this A is the vector potential. So that means your B is given by grad or curl of A. So we'll talk about all these things later. So that will give you, we have to modify that initial Landau's expression by introducing this additional term into that equation. So then 1950, there was another, this was the most active period in the superconductivity. So they even found something called the isotope effect. Isotope effect is if you have same atomic number, but your atomic mass could be different, right? So that means your number of neutrons will be different. So if we have mercury, so this you can see your atomic mass is different for this material going from 198 in going to 203. So they have different TC values. So it changes. We know mercury has about 4.15 around that value. But if you change your atomic mass by making the isotopes, so it actually changes from 4.12 to 4.18. So then if you look at the atomic mass versus TC, they are inversely proportional, but they found that TC to be 1 over m square root of m. So that's how this one is, right? So this is if you plot 1 over square root of this m, okay, this is the atomic mass, right? Versus TC, they show linear behavior. Also, this critical field also goes like 1 over square root of m. So this was the isotope effect. So that's basically changing your number of neutrons in the system. So then they 1950, so they tried to understand this Cooper pair situation. So then this is how they try to understand the interaction due to phonon mediation, right? If you have two electrons with momentum P1 and P2, so these two are supposed to get coulomically interacted, but because of mediation of a phonon, right? Remember we showed one electron will polarize the lattice, so that positive charges will attract the second electron. That means overall you have phonon interaction, right? So this electron phonon interaction changes your momentum of the your electron. So the one, so we can see for each pair will have different coming from this phonon mediation. You can understand like this. If this is my lattice, you have these two electrons. They have opposite spins and opposite momenta. So when they are moving, so because of this lattice distortion, that's a phonon, right? Because of that phonon interaction, these two electrons are supposed to be ideally repelled because they both are negative charges. Because of these phonons, so they try to stay together as a paired electron. That's the basis of this Cooper pair, right? So now you can see because of this phonon mediation, so they come together because this is how phonon allows them to stay together. So now the repulsion is no longer dominant, right? So the interaction become more dominant. That's how they stay as a Cooper pair. So then, yeah, this is the whole idea, right? So when this happens, if you take simple Fermi sphere, under certain condition, if this is my Fermi sphere, like Fermi wave vector Kf, so in standard metals, this Fermi sphere is very stable, right? You have all the electrons below Kf are occupied, all the state above Kf are all empty. But under this Coulomb interaction, this Fermi C become unstable. That means you can have some electrons even above Fermi energy, and definitely we have some below Fermi energy. That means your Fermi surface is no longer stable, but they all are very close to Kf. So it cannot be too away from Kf, very close to your Kf value. So important thing is this one, right? Your now V Coulomb and the V phonon, sum of these two should be effectively attractive, because Coulomb one is repulsive, but we know phonon interaction becomes attractive. So then the sum of these two should be attractive. So using this one, actually, BCS theory, that's very complicated. So I'm not going to talk about that one. Actually, Schrieffer managed to write this wave function for this many body system. So then you could solve the Schrodinger equation and find all these properties. So he calculated then this energy 2 delta T, 2 delta. So that is the energy required to break the Cooper pair. That goes like 3.52 times kBTC. And also this kBTC is related to this some coupling constant lambda. So lambda is given by, this is the electron phonon coupling parameter that is given by this equation. This has the density of states. So then also he could even get the results for that isotope effect. Tc goes like 1 over square root of m. So then yeah. So this, all these can be easily derived from that BCS wave function. So that all comes like I explained to you. This because this is my Fermi sphere EF, but you can have some electrons. So because in the Cooper pair you need to have one electron with minus k. That means there is moving in the opposite direction, with the other electron with the other direction, but they both should be within that H cross omega d. You cannot have the two electrons too far away from the Fermi surface. Also, we know these, if you take the Cooper pair, you have two positions and two spins, right? So they should have asymmetric wave function, right? Because these are still electrons. So they already make this pair as a yeah. So then they we know since these are singlet state, right? So we have actually in this case they show this is the total wave function that has both spatial and spin components. So that total wave function should be asymmetric, but we know for the spin part, so that is only sigma 1, sigma 2. So then this should, for the spin singlet, that means what? Spin singlet means you have asymmetric the spin part, right? That's a spin singlet. So that means your the spatial part should be symmetric. That's an even function. Spin singlet means you have symmetric because spin total 1 is 1, right? They are all in the same direction. They are symmetric. So then the total wave function should be asymmetric. Then the spatial part should be odd function, right? Because that should be asymmetric. Because everybody know the total wave function that has both spatial and spin, that should be asymmetric. So then if the spin part becomes odd, so then the other one should be other way around, right? So that's, you can understand. So then if you, in the BCS theory, we know you need to have a superconducting gap. If you don't have a superconducting gap, you don't have a supercurrent. So here you can see if you do the density of state versus, this is more like measuring the current. So as a function of your voltage, you can see there's no supercurrent. So in this region, because you have gap, right? So after we break the gap, you get this. So this is more like your 2 delta. So then we know how superconducting gap with the temperature. So gap is more like having your the critical field here. We know how to calculate all these parameters. So then in 1957, he discovered this principle behind this type 2 superconductivity. What he found was in these, we call sometimes dirty superconductors. So these superconductors, so they are superconducting in the bulk, but there are certain regions, like these regions, they are non-superconducting. That means we know superconducting part, you have the Meissner effect, your magnetic field cannot go through that. But if you have certain regions, they are non-superconducting, they are normal, then you will have flux lines passing through that, right? So that's what he found. There are some in the bulk superconductor, there are some regions we call the vortices, they are normal. So that means flux lines can go through that. So if you look at this one, you can see your magnetic field through this one of the vortices. So magnetic field is finite, right? It can go through, but if you go to the edge of that cylinder, it goes to 0, right? So that's more like a penetration depth. But if you look at the inside there, the order parameter or the superconducting density of state, that's 0 inside the vortex, but they become finite when it comes to the surface of the that vortex. So then you can see outside the vortex you have a supercurrent because you have superconductivity, but inside you don't have, that's a normal part, right? So if you look at the magnetism, magnetization, like we said, for the normal type 1 superconductor, if everything is superconducting, your M goes like minus H, that's a total perfect diamagnetism. But if you have this kind of type 2 or mixed state, so it doesn't go back to this one. So actually it shows this kind of behavior. So rather than it becoming 0 here, it becomes 0 after some, because it becomes 0 at this HC for type 1 superconductor, right? That's a critical field. But type 2 superconductors, it doesn't become 0, it maximizes at this point. So then it goes to 0 at this point. So we call this is like HC1 and this is HC2. So that's where the real critical field, right? You killed your magnetization completely. So then this part is called the mixed state. So you have the vortex states like this one. So if you look at H versus T, so you can see for the type 1, if everything is superconducting, you have this one. So at this TC, it becomes normal. But in the case of type 2, because of this vortex states, so here it becomes critical field, but still it is has some superconductivity because of this mixed states, right? Because you have these vortex states. So above this second HC2, it becomes completely normal state. So that's the difference between 1 and 2. But we can explain this superconductivity 1 and 2 in terms of this penetration depth and the coherence length. So actually this vortex situation is real situation. When you do this some magneto-optical imaging, you can see nicely, because if you do the magneto-optical imaging, you can observe the magnetic field, right? So these dots, they are the vortices, because through the vortices you have magnetic field penetrating through that you can see, but everywhere else they are superconducting, no penetration of magnetic field. So these bright white spots are the vortices. So even here you can see some, it's not very good image, but you can see the areas where these vortices are showing up. These are the places you have magnetic flux coming through. So here there are some other images used in scanning squid microscopy. So you can see the areas they have this magnetic flux lines are coming. These are the real vortices. So then when you go in the history, 1986, they discovered this high TC superconductors, this IBM group. This one, this is not the highest one, but because of that, people managed to get to this temperature above liquid nitrogen temperatures. So then it passed the nitrogen. So if you go through this history, then in 1962, Josephson found very interesting phenomena. If you have two superconductors, so they are separated by an insulator. So if you bring these two superconductors closer, that means you reduce this barrier width. So then you start seeing tunneling. So we know quantum tunneling, right? Electrons tunnel when you have narrow barrier. Here we are talking about this Cooper pairs tunneling through that one. Then he measured the tunneling current due to this Cooper pair tunneling. So then he found very interesting something called the Josephson current. So you can get a current even without applying any external bias because of this Cooper pair tunneling. But you need to make that barrier narrow enough. So this is basically a weak link between two superconductors. Weak link means if you have this order parameter in one side, they will tunnel through the barrier. So then you have same order parameter on the right hand side superconductor, then they are coupling together, right? So they are like interfering to wave functions or order parameters. So if you look at the absolute value and the phase of the order parameter, so you will see some change. So that means you have transport current passes through the junction. Then the interesting thing is, like I said, is mostly this Cooper electron pair tunneling through here. So what he found was, so even without any voltage, he found this tunneling current here. So there's no external field, but you have a current. But if you apply a current, you don't see any current here. If you apply voltage, you don't see any current. So that's why we call this a DC Josephson effect. So, but all of a sudden, if you go above certain voltage, it becomes non-superconducting. So then it shows standard linear IV characteristics. So this IJ is given by, actually it's varies as a sinusoidal term. So this chi1, chi2 are the, we'll talk about that one later. So that relates to your TC and everything. So then you can calculate your this this amplitude term IC. We are going to calculate all these things. Yeah, this is what we talk about, the weak link. So typically you need to get these two coming closer to each other. Then only you can have this interference term between psi1 and psi2. So basically your tunneling current is proportional to the probability, right, between psi1 and psi2. So you can calculate that. So we are going to do this one in more details between the leads. Yeah. So then a new development happens in 1973. They discovered the superfluidity of liquid helium-3. Previously, we talked about liquid helium-4, right? So that has a lambda point. So then below lambda point, it becomes superfluid. So, but liquid helium, that's actually, you have two protons and only one neutron, right? So that's why helium-3. So that's more like you have spin half fermion, right? So they actually, if you look at liquid helium-3, so they have two superfluid phases at high pressure and high temperature. You have something called superfluid phase A, then low pressure and low temperature, you have superfluid phase B. So they are actually happening below 2.4 and below 2. So this we can see here for high pressure, you have solids. So then high temperature, you have normal fluid. So when you cool it down, so below this one, you have superfluid A. So then if you cool further down, so then it becomes superfluid B. So like superfluid 3, you can say like condensation of pair of helium-3, because these are fermions, right? So then you can have two this helium-3 condensation as a pair because they are fermions. But in helium-3, they are bosons, so they condense as single atoms. So, but we know superconductors, they are Cooper pair, they are also condensing as Cooper pair, just like helium-3. So helium-3 and superconducted Cooper pairs, they have very some similarities. So in the next lecture, I will start talking about applications of these high temperature superconductors. So I will stop here.